Hello, hello, hello. Ciao, Matteo. Welcome back.
Hello, Luca. Ciao. How are you doing? I forgot to turn on the green. Here we go. We have the green. Hello.
Not too bad. Not too bad.
Not too bad.
Especially after we released our benchmark and, Amsterdam, where I was, and the market in general was extremely excited to see what we actually figured out. And I thought today was a great time because many people kind of like gave very interesting feedback, but at the same time, I think it was the right time and the right place to explain a little bit more on what went in our head when we kind of like decided to run this experiment.
So let's do a recap, Luca. You want to do a recap of what were the results of our benchmark, because maybe people have not heard about them.
Well, I hope that they read the title of this episode of today because that's the recap. But
okay.
In case they didn't and they joined this episode blindly or because they were forced by somebody, we found out that running VAT Next in VAT brings 93% performance improvement and brings down the error rate to 0.2%. And there's a caveat that we're going to explain in all this podcast, in this episode. That is the baseline that we created in our bencher. Many people ask about why we decided to go in a certain direction, and today we are gonna reveal the secret, like if it was a David Copperfield's show. So let's start.
Let's start. So let's explain the situation we want to verify, address, and show the difference. Okay. Now, the first problem of any Node.js CPU-bound application, okay, and all React server-side rendering frameworks suffer from the same kind of problem because of JSX, essentially.
Yeah.
They are CPU-bound activities, okay? And a rendering of an application can take, I don't know, maybe some megabytes of RAM alone, okay? Can be even 10, something like that. And on the other side can take, I don't know, 10, 20 milliseconds each. Now, if it takes 10 milliseconds to process an app, okay, so this is super fast, okay? Not really, okay? Because if you get, with 10 millisecond rendering, okay, if you get 1,000, okay, requests at the same time, you actually have a total time of 10 seconds to process them, and therefore, if the arrival rate is 1,000 a second, then we have a problem. Okay, you need to have at least 10 CPUs to process all of that. So what happens, okay, is whenever you have this kind of stressful situation where the number of incoming requests, okay, go over what your infrastructure can handle. Okay, this is, or it gets close to the breaking point of your infrastructure.
So the so-called saturation point, right?
The saturation point, okay. Exactly. So when you are getting close to the saturation point, your event loop utilization gets close to 1, okay, or it's 1, okay. You have no capacity left, okay. This means that whatever request will arrive at that time, it will be delayed for the future, okay? And the growth, as long as you keep that state of saturation, okay, the growth of the latency of the response starts growing hyperbolically on the growing of time. So after a certain amount of time, any new request that will reach that service will essentially never get a response in useful time. The user will refresh the page, Ctrl-R the page, because they think the system is stuck. Okay, so you have a saturation point. Okay, So you might a lot of people might say, well, but my infra will never saturate. Okay. First of all, this is everybody knows that this is essentially a lie. Okay. So infra can saturate all the time because you can reach whatever limit you have set. Okay. Because you will set a limit, otherwise your credit card will blow. So you need to say you will set a limit. Okay. Now the problem is at this point in time, you are hitting a limit. Okay. But anyway, even though if you cannot hit a limit, okay, you have a certain amount of period in which the elasticity of your infrastructure is going to be to expand the CPUs that are available of your system. This is typically called the autoscaler. In Kubernetes is the horizontal pod autoscaler, but similar concept exists in AWS, GCP, and so on and so forth, even for other system, other non-Kubernetes systems. It's irrelevant, to be honest, the tech at this point. You have a system that allocates more CPU for you. Okay. Now, and you hit the limit. Okay, and you start receiving a spike of traffic. You hit the limit. Now, once you hit that limit, okay, you are in. It can take, I don't know, a minute and a half, 2 minutes to start a new node process. Those are typical the time that you can see in practice in the system. Now, what happens in that period of time is a time of degraded service, essentially. Mm-hmm. And this is the source, a big crux of the problem. Most, given today, given today's market, okay, for a lot of businesses, it's very hard to predict when you will see a spike, okay? It can be that a post is going to be getting viral for whatever reason, but all of this is not easy to plan ahead. So they need elastic systems, right? But the moment you start getting attention, the system needs to scale up quickly. Now, this is the critical part, okay? Imagine that you send out, you do a campaign with an influencer, or some content you are publishing gets very popular, or you just publish a newsletter that performs extremely well, and people want to buy your things, your e-commerce stuff. Any of this, okay, can be the case. And you start receiving your service, your region, whatever, start receiving a spike of traffic, okay? And then it will take a few minutes to speed it up for the system for the infrastructure to respond increase, to it, right? To respond, okay? Yeah. Now, in this period of time, you need to start giving your user the best service that is possible, okay? And this means avoid saturation at any point in time, okay? Unfortunately, you can't avoid saturation, okay? Because if you receive all the requests, you receive all the requests, okay? In theory, we could potentially block them. I'm not saying that we're working on it. Maybe we are, but let's see what will happen in the future, okay? But so far with Node.js, is kind of impossible to prevent this from happening. Mm-hmm. Now, because it's impossible, okay, the request arrives, okay, and given that they arrive, now there is a decision to be made, okay, and the system is saturated, okay. Normally with standard Next.js, standard Node.js, PM2 cluster, whatever you name the system, okay. You can't really watch Node.js is not really very good at watching itself, okay? Because if it's busy doing all this server-side rendering, whatever interval or timeout that I'm scheduling will happen in the far future, okay? Yeah. And so, not good. So the solution, though, is relatively simple, okay? is kill it. Okay. But then we can't really kill it, okay? Because if we start killing them, our pod will fail, and to spawn a new pod, it takes minutes. So we can kill it. Whoop.
But sorry, Theo, we started kind of like talking about the saturation point, right?
Yeah.
And for our benchmark, we took a very strong arbitrary number that is 1,000 requests.
Yes.
Where does this come from?
So
let's help everyone understand the number.
Okay,
and then
the number, where does it come from? It could be 42 for all it mattered. Okay, it's that number comes from an analysis, okay, on the amount of request per second, the request per second that a Node.js server-side rendering process could do for that specific thing, okay, for that dummy page. And then because we were deploying to 3 pods, it was essentially, I did more or less a rule of thumb approximation, and it would become 1,000. Okay. You can imagine that, and that will cause saturation to happen, okay, without it being massive, overly catastrophic. Okay. So it's a specific point where, you think 3 pods with, 1 CPU, 6 pods with 1 CPU each could essentially handle 1,000 concurrent users. Okay. This is, you will think that is the case. And this is a hello world Next.js application. Okay. The simplest thing you can get. Okay.
And we decided to test on constant traffic. We didn't actually go for non-organic traffic.
No. Well, yes, exactly.
Traffic. And the reason is because we identified the saturation point for the machines we used to test.
Yes.
And we basically decided that we only test at saturation and not at
exactly.
spike,
I didn't want to test that. The actual real tests, okay, where these would be even more interesting, okay, is to have non-homogeneous traffic, okay? So have a few server-side rendered applications that are higher traffic, okay? Other that are higher CPU usage, other that are lower CPU usage, okay? Because not all of them are the same. And in no application, okay? So you need to test those 2 variants, also those 2 things, to make it a little bit more realistic, okay? This thing is realistic in the sense that it tests a very specific moment, which is saturation moment, okay? And it's a combination of the how Next.js 15 performs, okay, how Node.js 24 performs, how fast, how loaded are the physical machine where our VMs are running, okay? Yeah. So it's a combination of a lot of different things, and if we added more variants, it would have been harder to make a statement, essentially. So the reason where we wanted to say this is where saturation happened for this application. Each application is on its own, to be honest.
Okay. And so basically, just to kind of like close that chapter, we kind of like went for the kind of like Black Friday example, right?
Yeah.
So we kind of like tested, and I know that basically we are just over that period, but basically, so many people that might be listening that resemble with what we did. We kind of like went for saturation point. We found the limit of those machines, and we went for single node.
Yeah.
No multi-node, right? So this is a test that is done on a single node, single machine. Is it a single machine?
No.
Well, we have 1,000 requests, right?
Yes, it's one. Sorry, it's one machine making the request. The 1,000 requests.
Exactly.
Yes, yes. This is This is done on out of a single node. Okay, and going multi-node would be possible. Okay, but the more hardware we take is like even this was essentially saturating the network of the single node.
Yeah.
So I had to tune the kernel to be able to sustain the load or to be able to do what we wanted to do.
And what is the configuration we had in Kubernetes or in the machine?
In Kubernetes, we had 6 pods for single Next.js, 3 pods with 2 CPU each for VAT, our Node.js application server, and 3 CPU for PM2.
So you basically went for equal number of CPUs, different
Yes,
distribution.
exactly.
And in Next.js and in these cases, we just went for the default autoscaler.
There is no autoscaler involved in any of this.
Okay, so how, like, just for everyone to understand what was the mechanics behind?
It was just scheduled. So we spawned to our Kubernetes cluster with 3 nodes, okay?
Yeah.
And the 6 pods all the pods were allocated in those nodes.
And so default ingress, so round robin
Yes,
balance.
exactly.
Okay.
Exactly.
So there was no weighted routing, there was not weighted balancing. We're like pre-spawn machines with kind of like they replicate a setup, an old school setup of basically virtual machine with Nginx in front. Let's simplify
Absolutely, yes.
at the bare minimum.
Yes, I would say yes.
Okay, so given that baseline and given the kind of like our initial assumptions is that given the model that VAT has, because we kind of like reverse engineering the problem, our assumption is that VAT would have been better.
Well, to be honest, VAT was designed to solve this problem.
Correct. So our assumption is that VAT would actually have better results than anything else.
Yes. How does VAT solve the problem? Okay. VAT solves the problem thanks to 2 technologies. Okay. First of all, it uses multi-threading. Okay. So first of all, you need to solve the problem of how do you monitor Node.js from the outside. Okay. And we solve that problem by using the worker thread model. So the application is run as a worker thread, and the main thread acts as a watchdog for those applications. Okay. It monitors them, and it allows you to track down, and it allows us to track down if the event loop is being blocked, if the heap is growing too much, whatever. Okay, all the things. Then, if those thresholds are met, then, and after a few times that they keep being constantly being met, the worker thread is recycled in a soft way. So instead of crashing the pod or killing the pod, the thread is softly shut down and a new one is spawned. This is possible because of this capability in Node called in Linux called sorry_reusport that allows to open different sockets, but attached to the same TCP port.
Cool. So I can basically have one port with multiple threads behind the scene instead of the one-on-one linkage that Node kind of like taught us, right?
Yes.
Okay. And so, but how does this thing kind of like work behind the scene? Like, do we have the like, so it's kernel managed, right? In Linux.
Yes.
Okay. So basically, how does exactly work the mechanics behind the scene?
So the mechanics is a little bit convoluted. It allows us to essentially have multiple threads listening to the same port. Okay, so you can essentially have a hot copy of the same system. Okay.
Yeah.
What it does is whenever a new incoming socket arrives, it does a hash of the combination of host and port on both sides, okay, and it routes it to one of the given threads.
So it basically is doing some sort of like hidden netting between the port
it's
and
basically sending it to one, okay.
yeah.
Now once we have done that, or once you have done that thing, okay, we can if we are shutting down a server, okay, that server will stop listening to that socket.
Yeah.
Okay, so it can keep responding to all the incoming requests that it's already processing, but stop accepting new ones. So all the new traffic will only go to the new threads.
Okay. All the new traffic only go to the new thread. Okay.
So in this way, we can have, let's say if you have two CPU allocated, okay, the pod will always keep be functioning even if one of them of the threads gets completely blocked because the other one is available. Okay.
Yeah, so I can do hot swap also behind the scene of faulty threads. I can add more threads because the only thing that cares for the consumer is the port, and that's a facade that is going to be always live on the master process, right? On the main process. Okay.
Yeah, the main thread.
Main thread, yeah. Oh, yes, sorry, the main thread. You're right.
Yes. Now the monitoring can only happen because they will live in the same thread, in the same process.
So basically, the scope is the same.
Yeah, so because it uses some C++ API and shared memory space access to collect the metrics, to collect the data needed for doing these health checks.
Okay, so they share the memory space, ergo they can, because the main thread, that's what owns that memory space, right?
Yes.
Okay.
So well, not the thread. No, is the process. Is the process memory space. So the main thread has access to the worker objects, so it can send signals. It can even send an interrupt. Okay, I did this PR to Node.js core last year to be able to monitor the memory statistics from the outside. So I can. So this API sends an interrupt to the other thread, runs a bunch of C++ code in that thread, and then send it back.
Cool. And so, but exactly where is the kind of like, before we go into the findings and the mechanics of the findings, right?
Yeah.
You were actually mentioning about, traditional single CPU pods, PM2 multi-CPU pods, and VAT.
Okay, so it is the point, okay?
Why VAT is better?
In theory, single CPU pod versus multi-CPU pod should be the same, okay? Should deliver the same performance, okay? That's the theory, okay? In practice, with node cluster that is on the ARM technology and PM2, you doesn't work that way, okay? You pay a massive, a massive tax on any incoming socket. Well, because that socket needs to go to the main process, which the one that holds the cluster. Then it needs to go to that routes it to the childs. So to be honest, if you schedule 3 CPUs for your pod, probably you can only schedule 2 for your app, and you need to keep 1 for the main. So it's not effective, okay? So cluster is essentially a non-effective technology, okay?
There is a tariff to pay, just to tease.
Yeah, there is a tariff to pay, okay? If you want a system that can self-monitor itself, okay, and correct the problems, you need to... you have a problem like that to solve, okay? Now, VAT address this problem by using sorry use part, okay? So you can actually have the main thread working with the subthread, the child threads, and monitoring them from the outside, okay? It works. Then
so it's basically a kind of like a container model, right? So I have
yes, without the isolation, to be honest. So
yeah.
there is a limited isolation. Okay, it works. It's just multi-threading. Okay, to be honest, there is nothing more to say than that.
No, I mean it's basically the traditional application server kind of like model. You
Yeah.
have the main container, the main box that owns
Yeah.
all these worker threads that are managed between quotes by the main.
Yeah.
And but why is it better? Why do we get this performance? Where does this
Oh,
93%?
so the fundamental problem is the moment we realize that that system is completely broken, that that thread is completely broken, okay,
When you
we
say
can
broken, you mean saturated.
saturated. Yes, it's saturated.
It cannot.
It's
It cannot do
saturated.
anything
Okay,
anymore. Yeah.
we can shut it down, stop routing traffic to it, okay, and spawn a new one. Now, the net result of this is that the new one is fresh and performant. So instead of sending traffic to something that's never going to respond, you can get something good out of a new thread. Okay. This means that we cannot cancel error rate to 0. You will still get some errors.
Some errors, yeah.
Because we are like, in order to detect saturation, you need to reach saturation. So some request responses are never going to happen.
You need to trigger the saturation to fix the saturation. That's the kind of like the dog biting his own tail, right?
Exactly. So at that point in time, it just recycles itself, and that's it.
And where the other solutions are falling short then?
Okay, so PM2.
Yeah.
Where PM2 is falling short, node cluster. We covered it, okay? This kind of model is not viable with PM2 as it is today, or node cluster, okay? It's not viable. You can't do this, okay? You need multi-threading to be able to monitor from the outside.
Yeah.
Then you need something else, okay? Then there is so for that, I think it just self-eliminates, okay? Don't use node cluster, essentially.
Yeah.
Then you can there is one next step, okay, that you can do. And this comparison with with the single CPU comparison, okay? From there, the key problem is the failings of health check and the time it takes to spawn a new pod.
Yeah.
Okay. The time to detect that failure, okay, it's higher, okay, because I need to measure the fact that I'm sending a request and I need to experience a timeout or something. While if I monitor itself from within the process, we have via my nice memory space, same memory space APIs, okay, I can we can react at a much higher frequency, and check at a much higher frequency than you can do at the infrastructure level. Yeah. So the system actually can react way quicker when it detects saturation. And instead of watching it perform from the outside, it watches it unfold from the inside. And, it's given being close to the point of measurement, you can get more accurate data and make better decisions.
Okay, and now let's look at this kind of like trifecta, right? Because we mentioned 93% performance improvement.
Latency.
Latency, sorry. 0.2%. We get down error rate to 0.2%. But how are kind of like latency, throughput, and error rates connect with each other? What is the intersection point? How are they?
It's the saturation point. Okay, Luca, is when the three things interact. Okay, so the number of requests per second is so in this is a little bit of Q theory. Okay, if we are simulating a certain amount of traffic, okay, we are simulating that amount of traffic. Okay, in that level of simulation, okay, latency and throughput and failure rate are all connected to each other. Why? Because, if I am sending a certain amount of requests, okay, they will time out, of course, okay, but if I'm sending that amount of requests, then a higher latency reduces my throughput. I have fixed amount of requests. If they take more time, I'm transferring less data.
Okay, and so basically, these kind of like if we look at the kind of like macro picture, right? Because I think people they want to wear this. They're for sure thrown in this situation. We are looking at basically the traditional e-commerce world, right? Where you reach saturation. So our key is basically utilizing resources at top saturation point. And we identified at the top saturation point, we can still actually keep the error rate low on one side and still keep the throughput kind of like high at peak, having kind of like a still very acceptable latency. So in a nutshell, we are building more resilient systems that are tolerant to saturation point.
Exactly.
Right. So if I had to summarize in a sales and marketing sentence, how we would summarize our assumption, our goal with the VAT is that we make Node.js systems more resilient at their saturation point.
Yes, that we do.
So basically, what we discover with our benchmark is that we can still use, let's say, 90+% of resources at a higher level of efficiency, reducing the risk of failure.
Yes.
Right? Well, that's not bad. I mean, in an economy of saving money,
so it is that's the fundamental problem. Okay, it's Node.js works extremely well in steady state. Okay, but today's workloads are not steady state most of the time. Okay, they are dynamic, they spike, they change all the time. Okay, so and if the change is too quick, you need infrastructure, you need process to self-heal. Okay, you can't wait for, like, this is one of the fallacies, if you want to call it, of Kubernetes. Okay,
I think Kubernetes
of the liveness and readiness endpoints. Okay, it's not fast.
Well, but Kubernetes kind of like, in my opinion, and we voiced it several times, came with an assumption that is not valid anymore. Like the Kubernetes prefers high level of let's say for how Kubernetes and the world inside of Kubernetes was designed is that way better to kind of like have a multitude of very ephemeral systems than kind of like having to make systems that are more self-healing and stateful, between quotes. Right. So I think that philosophy worked phenomenally in the first area of microservices and the myth of
it's like, to be honest, it's about the fact, okay, that most Kubernetes systems are not fast to react to change.
No, but because they prefer a high level of distribution against a high level of tolerance. Right? Because if I have 100 CPUs and I distribute these 100 CPUs in 100 pods, right? I have a statistical kind of like chance that if this one roll is ephemeral, that the system has high level of resiliency, right? because I can distribute it more, right? But at the same time, I pay the price of not using all of these at 100%.
Yeah.
While what we are actually introducing as a concept, which I think how you describe it was extremely accessible and easy, is we don't leave anything on the table. We just have a system that prefers to have self-healing versus failure.
Yeah.
Because in Kubernetes, when you have this kind of like very tiny pod, you want them to fail fast, right?
Yeah.
Because they get decommissioned, and then you have a higher chance of distribution. So you cover the time of bootstrap from this distribution. But at the same time, like you just said, it's a fake sense of resiliency, because it's just like clearly they're dying. There's something new that comes in. It has time. It costs resources in the cluster. So, but if we had to kind of like close this conversation with some sort of like closing sentence and closing remark, right, on why VAT it's an enabler, right, for this new kind of like generation of web applications, and exactly what would be actually your closing sentence on why VAT is able to kind of like eliminate anything that is considered bottleneck and still keep high traffic under kind of like low error rate? So what would be your closing sentence? Our initial sentence was like the motto of VAT, and now how would you close? Why is VAT so powerful? How would you summarize it in one sentence for everyone? Today we also do a little bit of marketing.
That is an example of what modern Node.js can do. And a lot of applications are still stuck in the past. And I urge everybody to explore what capabilities have been added recently in Node.js and have been added at every single time. And we have spent a lot of time reasoning and making those work. So you can try that, but you can also explore those yourself, make prototypes, make ideas, see what are the challenges, and see for yourself, essentially.
Yeah, because when we launch VAT, and I think this benchmark is the perfect kind of like gem on the crown of that, where everything started. That is, we said that we were initiating this new revolution, or this new evolution of Node, right? We call it VAT because it was kind of like it was embracing the modern engines, the revolution that James Watt brought to the to the creation of modern kind of like industrial revolution. So for us, actually, this one is, I think, a great example. This benchmark shows exactly what we were saying basically 2 years ago. We're saying, hey, no, we all started, and you said it like very, very clearly. Node was designed and is extremely brilliant in constant load. It's great. It's like it's a workhorse, right? It's
Well,
going.
it's you can, as long as you don't hit saturation, you're great.
It's a perfect donkey, right? As we say, right? It carries weight and it goes. But in unpredictable traffic, in this new wave of modern applications. And to be honest, Theo, I cannot wait that one day we will be able to talk on the design that we made for this customer of ours using VAT in their AI ecosystem. Because I think we are opening this new kind of like world and say, people, AI is, we are all kind of like drawn by AI, right? You see API gateway saying AI is the new world enablement of consumer of APIs and so on, blah, 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 right? As we speak at probably reInvent, there were plenty of talks about this AI revolution. But what we are basically saying is that more than looking at the AI revolution, look at the foundational piece behind the scene. We are changing architecture, we are changing expectation from applications. Users have different expectations, but they still keep the same single expectation on websites. It has to be fast and it doesn't have to crash, or else I need to refresh or leave the website and go somewhere else. So basically, you and I were joking about that, but we said, what is an antidote to some sort of like problems that are emerging right now, right? Is some sort of penicillin to these kind of like new applications, but at the same time helps really people, not people, but companies and users and developers in this kind of like environments like e-commerce or like a modern LLM and so on and so forth, to kind of like keep responsiveness to their users, which basically directly converts into lowering the expected churn that traditionally would have against non-responsive applications. So that's kind of like the big picture that we are giving. But yeah, I think we are at time, Theo. I think it was a great chat. I cannot wait to chat again next week. And till then, I think we are inviting everyone to challenge our benchmark, give us feedback, open the conversation. We are here to have a chat, and you know where to find us. We would love actually to discover, is what we actually brought to the market solving one of your headaches? And if so, let us know how. Ciao, Theo. See you
Bye,
next week.
Luca.
Ciao, everyone.
Ciao, ciao, ciao,
Bye
ciao,
bye.
ciao. Bye.